So we've been talking about systems of linear differential equations. And on Tuesday, I was kind of building the connection that our solutions, like our general solution for a system of linear differential equations, comes from exploiting the fact that we already know how to solve something that looks like dy dt equals a constant times y. We were like doing that back in chapter 14 stuff. And then connecting that with the eigenvalue, eigenvector stuff, I know that multiplying a vector times a matrix is the same thing as multiplying it by a constant, specifically if we're talking about eigenvalues and eigenvectors. So there's kind of two parts to this process. If I'm trying to solve a system of linear differential equations, I'm going to have to put it into a matrix form. I'm going to have to find the eigenvalues and the eigenvectors, which lets me write the general solution. That's kind of the mechanical stuff, and we can practice finding eigenvalues and eigenvectors. But I actually think that the harder part for most students is the two things that you're being asked to do on these homework problems. The first one is sketching solution curves in a phase plane, and just generally most students are less comfortable graphing. And then finding solutions. So I'm going to start with those two kind of skills in this warm-up problem, and then we can go back through the entire process. So our general solution to a system of linear differential equations is going to have this form that looks like a constant times e to the lambda t, lambda being our eigenvalues, times the eigenvector. And we're going to have that because for a 2x2 system, I've got two eigenvalues and two eigenvectors. I'm going to have two parts to my general solution here. So if I have to sketch the eigenlines and solution curves, we're going to start by getting ourselves a plane and sketching the eigenvectors and just extending that forever into a line. So here, my first eigenvector is the vector 1, 1. So if I sketch a vector 1, 1, but I just continue that forever in both directions, that's my first eigenline. Now, I know because these are paired up that this eigenvector goes with an eigenvalue of -2. So I'm going to go ahead and just write that on here. If I look at my other one, I sketch the vector 2, -1, that says move 2 to the right and down 1. So 2 to the right, down 1, that's going to look something like this. So 2 to the right, down 1. And the eigenvalue associated with that one is 3. So I'm just going to write on here, lambda equals 3. So now comes the fun graphing part. So along the eigenlines, I'm either going to be going towards the equilibrium of 0, 0, or away from the equilibrium of 0, 0. And the way that I can tell that is by looking at my general solution and thinking about what's going to happen as t approaches infinity. So this first piece associated with that eigenline for 1, 1, as t approaches infinity, this is going to go to 0 because e to the negative infinity is headed to 0. So that means that along the eigenline associated with lambda of -2, I know that my solution curves would just head straight in to 0, 0. Now I'm thinking about my other eigenline. So along the eigenline associated with this eigenvector of 2, -1, as t approaches infinity, this piece is going to get infinitely large because e to the infinity goes to infinity. So that means I'm going to be headed away from the equilibrium of 0, 0. So that's what my solution curves look like if I actually start exactly on one of the eigenlines. everywhere else, I'm going to be influenced by both of the eigenlines. For this particular one, because I have one positive eigenvalue and one negative eigenvalue, I know that the equilibrium is a saddle. And so what those solution curves are going to look like, if I start somewhere over here, I'm going to be getting pushed in towards the origin, but at some point I'm going to have to flip and get pushed out along that other part of my trajectory. If I started somewhere in here, the arrows near me, like thinking about our vector fields, my arrows near me are kind of pushing me in towards the origin, but at some point I'm going to turn and get pushed out this way. If I were to start over here, again, I'm going to get pushed in towards the origin by those arrows and then pushed out. Over here, if I got pushed by those arrows, I would get pushed in and then pushed back out. So that's what some possible trajectories or solution curves would look like. Now and that's the part that obviously we can't really put into web work. It just says that you should sketch several solution curves in the plane. So that's what that sketch would look like. The next part that we're asked to do is to actually find the particular solution, which just like we were doing with like single differential equations, finding the particular solution means I'm going to use the initial condition I was given in order to find the constants. So here, the initial condition that I was given is that when t is equal to 0, x equals 3 and y is equal to 0. So I'm going to use those in my general solution. So my general solution says that I should be at 3, 0 when t is 0. So I'm just plugging in 0 for t, plugging in the values I was given for an initial condition. It doesn't really matter what tools you use to solve this. You could put it into an augmented matrix and row reduce it. I'm just going to write the set of equations out. Since e to the 0 is equal to 1, I'm just going to kind of read across the top row. So I would have 3 is equal to c1 times 1 plus c2 times 2. And then reading across the bottom row, 0 has to be equal to c1 times 1 plus c2 times -1, or minus c2. And now I can solve that however I want to solve it. I'm going to choose to subtract the second row from the first row. So 3 minus 0 is 3. C1 minus C1, it's gone. And 2C2 minus -C2 gives me 3C2, which means that C2 has to be equal to 1. And knowing that, I can look at either of the equations to get the value for C1. The second one looks cleaner to me. So if C2 is 1, C1 must also be 1, which means my particular solution looks like plugging in the 1 and 1 back in here. So I'm going to say that our XY vector, which also the notation in web work is just an X with a vector symbol. So if I were writing this as a vector, I would say that my XY is equal to C1 was 1. So that means I'm going to have e to the -2t times the vector 1, 1. C2 was also 1, so plus e to the 3t times the vector 2, -1. And just as a note for how we're putting that into web work, web work is kind of asking us to break that up into the x equals equation and the y equals equation. And we're going to do that by just sort of reading across the top and the bottom. So if I write these separately, that means x would equal 1 times e to the negative 2t plus 2 times e to the 3t. And y would equal 1 times e to the negative 2t minus e to the 3t. Our eigenvalues, we brought our eigenvectors, so we can write our general solution, figure out what our particular solution is. So in terms of my general solution, I'm gonna have C1 e to the, I'll take the positive 3 first, so C1 e to the 3t times 1, 1, plus C2 e to the negative t times 1, negative 1. Are those okay as eigenvectors, or did you want me to pick something else? That'll work? Okay. So our initial condition of 4, 2 means I've got C1 times 1, 1 plus C2 times 1, negative 1. Because when I plug in 0 for t, e to the 0 is 1. Good with that part, right? Okay. So now, just kind of reading across the top row, I've got 4 is equal to C1 plus C2. 2 is equal to C1 minus C2. And if I add straight down, 6 is equal to 2C1. C1 is 3. And if C1 is 3, then C2 has to be 1. So now I've got my constants to plug in. I'm just going to plug them in. So my C1 was 3 and my C2 was 1. Okay. So in terms of kind of writing that out, that means what's going in is x should be equal to, and I'm just kind of reading across the top here. So 3 e to the 3t plus e to the negative t, and my y should be 3 e to the 3t minus e to the negative t. Okay. Set this up as a matrix equation to say d dt of an x vector is equal to the matrix -2, 1, 1, -2 times my vector x. And the whole idea is that multiplying a matrix times a vector is equivalent to multiplying the vector by a constant if that lambda is an eigenvalue. So we're going to find those eigenvalues by looking for the determinant of a minus lambda I and setting that equal to 0. So I'll walk through this first one and then I'll get you more for practice. So I'm looking for the determinant of -2 minus lambda, 1, 1, -2 minus lambda. And I'm hoping I didn't mess anything up and it's going to factor. So that determinant, I've got -2 minus lambda times -2 minus lambda minus 1 times 1. Okay, moment of truth. Lambda squared, that's a +2, another +2, so +4 lambda plus 4 minus 1 is +3. I think that factors. So I've got lambda plus 3 times lambda plus 1. So I can already classify my equilibrium. If both of the eigenvalues are negative, then my e to the lambda t terms are both going to 0. So I know that this is stable. And I can call this a stable node, or our textbook also uses the word sink. So it's a stable node or a sink at 0, 0. Once I have the eigenvalues, then I can go back and find the eigenvectors. A couple of different ways to find the eigenvectors. I'm going to stick with plugging the values back into the matrix equation. So if lambda is equal to -3, then I have -2 minus -3, 1, 1, -2 minus -3 times my vector xy has to be equal to 0, 0. So -2 minus -3 would be a +1. So I've got x plus y equals 0 for the top row. And the bottom row says exactly the same thing. X plus y is equal to 0. They should not have conflicting information in the top and the bottom row. So in terms of that eigenvector, I can choose anything I want to plug in for x. I'm going to choose 1, and that's going to make y -1. By the way, this is the equation of the eigenline. So if I'm sketching the solutions, that's the equation of my eigenline that I need to sketch in order to draw solution curves on my phase plane. We'll sketch in a second. For now, I'll just find our other eigenvector. So if lambda is equal to, what was my other one? -1. Then my matrix equation, I'm going to try to do math in my head and try not to mess it up. So 2 minus -1 is going to give me -1, 1, and then 1, -1 for that bottom row. Which means -x plus y is equal to 0. Or if you want to write the second line, x minus y is equal to 0. Same thing. This is my equation for the eigenline. And if I choose an eigenvector, never unique, every value of x you want to plug in is equally good. I'm going to choose to plug in 1 for x, and that's going to mean that y has to be also 1. Now I'm ready to write the general solution. Once I have my eigenvalues and eigenvectors, then my general solution always takes the same form. C1 E2, and it doesn't matter which lambda you put first. So I'm going to have this as C1 e to the -3t. What does matter is that you make sure that the eigenvector you write matches which eigenvalue you put. So the eigenvector that goes with -3 was 1, -1. And the eigenvector that goes with a lambda of -1 was 1, 1. So that's my general solution. And here I didn't give us an initial condition, but let's go ahead and sketch the phase plane to see what some of those solution curves are going to look like. Because I do think that is something we're expected to do. I know it is, because when we get to the nonlinear systems, we're definitely going to do phase plane analysis. So we have to be able to sketch this phase plane. So I'm going to go back and sketch our two eigenlines. So the first eigenline that went with lambda of -3, that eigenline was y equals -x, or you could take the eigenvector and just plot the eigenvector that says 1 to the right, down 1. So there's my eigenline that goes with lambda equals -3. And my eigenline that goes with lambda equal to -1 is, I can either think about it as that vector, 1 to the right, up 1, 1, 1, or I can go back to the eigenline equation, which I could also rearrange to say y equals x. So that was for my lambda of -1. So along the eigenlines themselves, both lambdas are negative. So I know my trajectories just head straight in to the origin. And in fact, because this is a stable node, all of my trajectories head straight into the origin. So everything's just headed into the origin here. I don't think they're going to get too picky about what those trajectories look like. Really what we're looking for is it a saddle? So do I have trajectories that kind of start to go in and then bend out? Is it a sink? So everything's headed into the middle, or is it an unstable node and everything is leaving the middle? Walking up to the system of differential equations. If I'm trying to find the general solution or classify stability, I have to start by getting my matrix of coefficients. So 3, 1, -2, 0. And so finding those eigenvalues, I'm looking for the determinant of 3 minus lambda, 1, -2, 0 minus lambda. So 3 minus lambda times negative lambda minus -2 times 1. Lambda squared minus 3 lambda plus 2. So I get lambda. Perfect. So if my lambdas are 2, +2 and +1, then I already know that this is an unstable node, which our textbook also calls a source. Once I've got my eigenvalues, next step, I've got to find the eigenvectors. So when lambda is equal to 2, if I plug that in, my matrix equation becomes, so 3 minus 2, so 1, 1, -2, -2. Great. Top equation, bottom equation say the same thing. So if x plus y is equal to 0, then that eigenline is the line y equals -x. And an eigenvector I could use is 1, -1. You don't have to choose the same eigenvector, but that's what I'm going to choose. If lambda is equal to 1, that matrix is going to look like, so 3 minus 1 is 2, 1, and then -2, -1. Great, they're going to tell me the same information. So 2x plus y is equal to 0. So my eigenline is y equals -2x. And I'm going to choose the eigenvector 1, -2. So I can either do the sketching or write the general solution. I'm going to go ahead and sketch it. So I'm going to start by graphing my 2 eigenlines. And this time they both have a negative slope. So I'm going to have a slope of -1 and a slope of -2. So this is my eigenline where lambda equals +2. And this is my eigenline where lambda equals +1. So along those 2 eigenlines, because they're both positive, I know we're moving away from the origin. And if I made other trajectories, all of the trajectories are going to move away from the origin. If I go to find the general solution is always going to have the same form for our linear systems. So I'll have C1 e to the 2t times my eigenvector 1, -1 plus C2 e to the t times my eigenvector 1, -2. Now here's why it doesn't matter what you choose for an eigenvector. Whatever you choose it's going to be a scalar multiple of one of my eigenvectors. So when we go to solve for the particular solution, it's just going to mean that my constants won't match your constants. But if we multiply it all out, we'd get exactly the same thing. So I'll just stick with these. So for the initial condition, x equals 1, y equals -1 when t is equal to 0. I'm going to have c1 times 1 -1 plus c2 times 1 -2. And I'm going to choose to just write that as a system of equations. 1 is equal to c1 plus c2, and -1 is equal to -c1 minus 2c2. So if I just add those together, I get that c2 is 0. And if c2 is 0, then looking at the top equation, c1 must be equal to 1. Now, there's a reason that c2 is going to be 0. Because if I look at this, I chose an initial condition that is already on my eigenline. I chose an initial condition that's already my eigenvector. So I probably didn't actually need to write that out. I just wasn't clever enough to notice that at the beginning.
But is that always the case?
No, I mean, it wasn't the case in the last one we chose. But it can happen. And if it does happen, then when I go to write my particular solution, it means that I'm going to leave off that whole piece from the other.
But it's also correct,
Okay. Yep. So I'm going to leave this whole piece off. So my solution is just going to look like, since c1 was 1, e to the 2t times 1 -1.